This video will cover econometric models with interaction variables. At the end of this video, you should feel comfortable specifying an interaction model appropriate for answering a given question, making predictions in a model with interaction variables, and interpreting the coefficients of an interaction model. Let's build on the topic of gender differences in the labor market first introduced in the video on dummy variables. Does education benefit women or men more in the labor market? Perhaps understanding the role of education might help us to understand gender differences in labor market outcomes. What data will we need to address this question? If we had a sample of individuals, we need some relevant labor market outcome. While there are many possible outcomes, let's use annual wage and salary income, in other words, income earned from working, measured in dollars. We'd also need to know their gender, which we can represent using a dummy variable. Finally, we need to know the education level, which we could measure as the number of years of education completed. Shortly we will see that addressing the above question will require a new twist to our econometric model, but let's first see what we can learn from a simple one. Our motivating question suggests that income should be the dependent variable, while gender and education are the independent variables. Let's estimate this model using a sample of employed individuals from the Current Population Survey, or CPS. Here are the estimates of our first model. Take a moment to interpret each of the coefficient estimates. The estimate of beta 1, the female coefficient, tells us that women earn on average more than $20,000 per year less than men with similar levels of education. This is a reminder of the gender pay gap explored in the video on dummy variables. The estimate of beta 2 tells us that an additional year of education is associated with an additional $6,600 in annual income, holding gender constant. We could also think of beta 2 as the marginal effect of a year of education on annual income. We should add the caveat that we can't be sure the estimate reflects only the causal effect of education, but that distinction is not the focus of this video. With those interpretations in mind, let's revisit our motivating question. Does education benefit women or men more in the labor market? It doesn't seem that this model helps us to answer this question. Beta 1 told us something about the gender gap in income conditional on education, while beta 2 told us the marginal effect of education conditional on gender. We could rephrase our question by asking, how does the marginal effect of education differ for women and men? The linear model does not tell us this difference in marginal effects, but we will see that adding a variable to this model will achieve this objective. In the new model, we've added a variable that is the product of the female and education variables. This may sound like a strange variable to create and add to our model, but it turns out that this new variable will make the model more flexible in the way that we need to address our questions. This additional variable is also called an interaction term. As we will see, the coefficient on this variable will tell us how gender and education interact in their relationship with income. Let's explore the mechanics of this new interaction model. To estimate such a model using statistical software, we will generally need to create a new variable in the dataset equal to the product of the two variables of interest. Here we use an underscore in the new variable name to indicate that we are multiplying together the female and education variables. When we think about these two variables, it may seem strange to multiply them together, but that's exactly what an interaction term does. Note that for any male in the dataset, the zero value of the female variable means that the interaction term is equal to 0 regardless of the level of education. With a new variable created, we can then estimate the model. Here are the results of estimating the model. We could represent these results by switching from the population model to the sample model, and by matching up each of the variables, substitute the numerical values of the coefficients. Ultimately, we would like to be able to interpret each of these numerical values, but it may not be obvious how to do that. For example, note that we cannot interpret the education coefficient as the effect of an additional year of education holding all else constant, because increasing education by 1 would also change the values of the interaction variable. To better understand the meaning of the model's coefficients, let's start with a more straightforward task, making predictions in interaction models. Because gender takes on only 2 values in the dataset, an easy place to start would be to predict the income separately for women and men. Note that in each case, we will not choose a specific education level, instead keeping that variable in our predictions. For women, we can make a simple substitution in the model. The value of the female variable is 1, so the second term simply becomes beta 1 hat. We can also substitute a 1 for the female variable within the interaction term, so that this final term becomes beta 3 hat times education. Together, we have the following prediction. We can simplify this slightly by grouping together the 2 intercept terms and grouping together the 2 education terms. We can also repeat this process for men. In the model, we can substitute 0 for the female variable in 2 different places so that the 2 terms disappear from the model entirely. These predictions will soon help us to give some insight into the model's interpretation. Take a look at the predicted incomes for women and men. Notice that each equation is a linear function of education. Those lines have different intercepts for women and men, and they also have different slopes. In other words, our interaction model has predicted that men and women have incomes that are 2 different linear functions of education. To better understand these predictions, let's plug in the model's numerical estimates. Returning to our equation for the predicted income of women in the sample, we can also substitute the numerical values in for each of the beta hats, and then simplify this linear function. We can then repeat again for men, again plugging in the relevant numerical values. With these predictions in hand, it would be useful to see the results graphically. Here we graph the predicted income of women and men as a function of education. Note that each prediction is a linear function of education, and that the lines have different slopes and intercepts as predicted by the model. In a moment we'll discuss what this tells us about our motivating question, but first let's think about the graphical meaning of our model's coefficients. Here are the equations for the predicted incomes again, this time leaving in the beta hats to represent the sample parameters rather than using their numerical estimates. The beta 2 hat in the prediction for men is the coefficient on the education variable. Since this is a linear equation, that beta 2 hat is also the slope of the predicted income education line for men. Similarly, the coefficient on education in the equation for women is beta 2 hat plus beta 3 hat, and this sum is also the slope of the predicted income education line for women. We could also note that the beta 3 hat is the quantity that we added on to the slope for men to obtain the slope for women. In other words, beta 3 hat is the difference in slopes between women and men. Now that we've looked at the slopes of the prediction lines, let's also take a look at the intercepts. To better see the intercepts on the graph, we'll extend the horizontal axis of the graph to include 0 years of education. As is often the case when examining intercepts in linear models, these predictions don't make sense because we are extrapolating too far out of the sample. We would not expect to see negative incomes, but we also would not expect to see people with 0 years of education in a recent dataset on residents of the United States. For a moment, let's gloss over this problem and interpret the intercepts literally. In the equation for men, we can see that beta 0 hat is the intercept of the line. Literally, this would be the predicted annual income for men with 0 years of education. Similarly, in the equation for women, the intercept of the line is beta 0 hat plus beta 1 hat, which is also the predicted income of women with 0 years of education. Finally, note that beta 1 hat is the amount that we add to beta 0 hat, the intercept for men, to obtain the intercept for women. In other words, beta 1 hat represents the difference in intercepts between women and men. Let's return to our interaction model and summarize what we've learned about the interpretation of each coefficient. Beta 0 hat, the interaction model's intercept, is the intercept for men in the income-education relationship. beta 1 hat, the coefficient on the female variable, is the difference in intercepts between women and men. Beta 2 hat, the coefficient on education, is the slope of the income-education relationship for men. Finally, beta 3 hat, the coefficient on the female education interaction variable, is the difference in slopes between women and men. Let's apply these interpretations to the numerical estimates of our model's coefficients. The model's intercept is also the intercept of the income-education relationship for men, so that men with 0 years of education, again remembering that this is an out-of-sample extrapolation, are predicted to earn negative $51,559 per year. The estimated female coefficient is the difference in intercepts, so that women with 0 years of education are predicted to earn $16,056 more than men with 0 years of education. The education coefficient is also the slope of the income-education relationship for men, so that an additional year of education increases men's annual earnings by $7,762 per year. Another way of thinking about this value is that it's the marginal effect of education on earnings for men. Finally, the interaction coefficient is the difference in slopes for women and men, which we could also think of as a difference in marginal effects. That is, an additional year of education increases women's annual earnings by $2,639 less than men on average. Think back for a moment to the question that motivated the interaction model. Does education benefit women or men more in the labor market? The coefficient on the interaction variable answers this question directly. Women on average are seeing a smaller benefit than men in terms of annual earnings for each additional year of education. We also saw this on the graph of predicted incomes. We could see a gender gap in earnings for a wide range of levels of educational attainment, but that gap actually increased at higher levels of education. Although we should be cautious without more detailed evidence, perhaps one reason for this result is the differences in the disciplines that women and men tend to study in college. This might support the argument that one important step in narrowing the gender pay gap is to encourage women to study fields with greater earnings potential, including science, technology, engineering, and mathematics, or STEM fields, and, if you don't mind my suggestion, economics. With this idea in mind, let's take one more look at our motivating question. If the gender differences in the benefit of education is driven by college, we could consider modifying our analysis to focus on the receipt of a bachelor's degree. Let's use the same two variables for income and gender, but let's replace the continuous education variable with a dummy variable equal to 1 if the individual completed a bachelor's degree and 0 otherwise. To focus on the benefit of an undergraduate education, we will limit our data set to individuals with a high school diploma but no college, and individuals with a bachelor's degree but no graduate school. Because we are interested in knowing the difference in the benefit of a bachelor's degree for women versus men, let's again use an interaction model that contains the variables for gender and education, as well as the interaction between those variables. One key difference between this model and the previous model is that we have replaced the continuous variable for years of education with a binary variable for having a bachelor's degree. In other words, this is an interaction model with two dummy variables. Here is the sample version of that same model. We will look at the numerical estimates of the parameters in a few moments, but let's attempt first to understand the model by taking a familiar approach, making predictions. Note that the model only has two distinct binary variables, and there are only 4 possible combinations of gender and education, so it would be straightforward to represent the predicted outcomes of these 4 groups in a 2x2 table. In the top left corner of the table, we will write the predicted income of a female with a bachelor's degree. In our equation, we can substitute 1 for the female variable and also 1 for the bachelor's variable. Since all coefficients in the model are multiplied by 1, the predicted income is beta 0 hat plus beta 1 hat plus beta 2 hat plus beta 3 hat. The top right of the table will have the predicted income of a male with a bachelor's degree. So we can substitute 0 for the female variable and 1 for the bachelor's variable. Now the beta 1 hat and beta 3 hat terms are multiplied by 0, so we are left with beta 0 hat plus beta 2 hat for the predicted income. In the bottom left, a female with no bachelor's degree has female equal to 1 and bachelor's equal to 0, so the predicted income is beta 0 hat plus beta 1 hat. Finally, in the bottom right, a male without a bachelor's degree has a value of 0 for both the female variable and the bachelor's variable, so the predicted income is simply beta 0 hat. We will use this table of predictions to help us understand each of the coefficients in the model. For example, we can see that beta 0 hat represents the predicted income of men without a bachelor's degree. To get a better sense of the remaining coefficients, let's draw some comparisons across cells in the table. For example, if we focus on men and calculate the difference in predicted incomes between those with a bachelor's degree and those without, we see that this difference is beta 2 hat. In other words, beta 2 hat tells us the additional earnings associated with a bachelor's degree for men. The analogous earnings boost for women is beta 2 hat plus beta 3 hat. Next, note that we could also examine differences in the other direction. Among those without a bachelor's degree, the difference in predicted income between women and men is beta 1 hat. In other words, beta 1 hat tells us the gender pay gap among those with a high school education. The analogous gender gap for those with a bachelor's degree is beta 1 hat plus beta 3 hat. Finally, note there is one remaining cell at the bottom right of the table. We have predicted the additional earnings associated with the bachelor's degree for women and also for men. How much does this earnings boost differ between women and men? Subtracting the two, we can see that the answer is beta 3 hat. Mechanically, we also could have arrived at the same answer by comparing the gender pay gap among those with a bachelor's degree versus those without. For reasons that should now be obvious, the interaction coefficient beta 3 hat is also sometimes called the difference in differences. This quantity often helps us to answer a question that would not have been possible without an interaction model. To further develop our intuition for the meaning of all the model's coefficients, let's add numerical values. Here is the model with numerical estimates substituted for the sample parameters, along with the numerical dollar amounts corresponding to each of the predictions that we just made. Let's take a moment to interpret each of the values in the bottom row in the rightmost column. First, the difference for the female column indicates that women with a bachelor's degree earn $21,862 per year more than women without a bachelor's degree on average. Moving one cell to the right, also the beta 2 hat estimate, is the analogous earnings boost for men. That is, men with a bachelor's degree earn $34,847 per year more than men without a bachelor's degree on average. We can compare these two values using the difference in differences. This value tells us that the annual earnings boost associated with the bachelor's degree is $12,985 less for women than for men. Note that this difference in differences also answers our motivating question. Although women and men both appear to benefit from earning a bachelor's degree, the benefit for women is smaller. We could also examine these differences in the other direction. The difference column for bachelor's degrees recipients tells us that women with a bachelor's degree earn $25,115 per year less than men with a bachelor's degree. Just below that value is the analogous gender gap for those without a bachelor's degree. Women without a bachelor's degree earn $12,130 per year less than men without a bachelor's degree. Finally, we can return to the difference in differences with an alternative interpretation by noting that the gender pay gap differs based on educational attainment. The female-male gap in annual earnings is $12,985 greater in magnitude, that is, more negative, for bachelor's degree recipients compared to individuals with a high school diploma. finally, we'll conclude by noting the unique information that we can learn by estimating an interaction model, and in particular by interpreting the coefficient on the interaction term. First, interaction models are useful for estimating differences and marginal effects between groups, as we saw in the model with an interaction of a binary variable and a continuous variable, in our case gender and years of education. Second, interaction models are also useful for estimating differences in differences within two pairs of groups, as we just saw in the model with an interaction of two binary variables, gender and receipt of a bachelor's degree.